So welcome everyone to the last module remaining in this course, that is partial differential equations. And yeah, well done to all the students who've made it this far. I feel like this is the crux of this course, and it's one of the most powerful modules to learn because partial differential equations have widespread applications. For example, in groundwater flow, say we have a water reservoir that looks something like this. We can describe the flow potential lines by the Laplace equation, which is d squared h dx squared plus d squared h dy squared equals 0, which is also written as del squared h dot. There's other examples. Deflection in beams could be written as del squared h equals some forcing, and the one-dimensional wave equation, which is written as partial derivative of h with respect to time squared, is equal to some constant d squared h by dx squared. Okay, so here we're talking about equations that involve partial derivatives of two or more independent variables. And some important terms for you to remember is that the order of a partial differential equation is the highest order of the partial derivative. Here in this chapter, we're only going to be looking at linear second order equations, which brings me on to the next term, which is linear. All right, so a linear PDE is one that is linear in the unknown functions and all of its derivatives with coefficients depending only on the independent variables. In other words, what I mean by this is, say we had the partial derivative for function u x y, so d squared u by dx squared plus 2xy d squared u dy squared plus u equals 1, for example. This would be a linear partial differential equation because the coefficients depend only on the independent variables, that is x and y, and well, u is a function of x and y. An example of a nonlinear equation is simply d squared u dx squared plus xu du by dy equals x, or d squared u dx squared or cubed plus 6 d cubed u dx dy squared equals x. Here the nonlinear terms arrive because the coefficients are they do not depend on the individual variables themselves. Try and get your head around why this term would be a nonlinear term. All right, so in general, we can write a second order linear partial differential equation as a of xy multiplied by d squared u dx squared plus b of xy d squared u dx dy plus c xy day squared u day y squared plus d, which could be a function of x, y, du dx, and du dy, and u. Okay. Now, the classification of the second order linear partial differential equation is based on the sign of the discriminant. So the discriminant being b squared minus 4ac, we have the following classifications. So let's just write classification and an example here. If we have, for example, that the discriminant is less than 0, then our classification is that of an elliptic partial differential equation, and an example would be the Laplace equation. Day squared phi day x squared plus day squared phi by day y squared equal to 0. Very similar to ground water flow. If the discriminant is equal to 0, we have a parabolic partial differential equation. An example is diffusion, where the partial derivative of the concentration with respect to time is equal to some constant day squared c day x squared, where c is our concentration. If the discriminant is greater than 0, we can classify our PDE as a hyperbolic partial differential equation. And an example would be the wave equation, which is d squared phi dx squared is equal to c day squared phi by day x squared. Now the wave equation in this instance is only looking at one spatial dimension, and the wave equation can be extended to two different spatial directions, and it is a very important equation when in fluid dynamics.